All right, hello everyone. Today we're going to start talking about power series. So in 11.2 through 11.7, we were looking at series like this, right? Let's start this series at 0. We're going to be doing a lot of that from now on. And so what is our series? It's adding up an infinite amount of these terms, Cn, where each Cn is a real number. So we're adding up an infinite list of numbers. Okay. So in these previous sections, we had a couple of questions we asked about each series. First, we asked, does it converge, right? And then if it converged, we asked what was the sum, and we couldn't always figure out what the sum was, but all convergent series have a sum. Okay, if a series converges, it does add up to some number, but we only have a formula for that number in special cases, right? Like the geometric series. Okay, so we could always ask, what is the sum? What is the value? Maybe sometimes this question isn't easily answered, but these series always have sums, right? Now let's look at a different type of series, the power series. Okay, so what does a power series look like? It's going to look like this. Okay, so I'm writing it in the most general form first, and then we're going to talk about a specific form. But we have Cn times x minus a to the power n. So what does all this mean? These CNs and this A are they're just real numbers. Okay, so just like in this series, the CNs are real numbers. And then we have this variable here, X, and then we have this real number A. And then this X minus A is to the power N. Okay, so maybe this doesn't make any sense to you, but think about what this series looks like over here, our normal series. Okay, if we were going to expect, what does this notation mean? It means we're adding up C0 plus C1 plus C2 and so on. So we could write this as C0 plus C1 plus C2 plus forever. And what would this power series look like? It would be C0, x minus a to the power 0. That's just, let's see, anything to the power 0 is just 1, right? So that'd be C0 times 1, which is just C0, plus C1 times x minus a, plus C2 x minus a squared, plus dot, 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 on forever. Okay, so this series is, we're adding up a infinitely long list of numbers, and then this series is, it's kind of like an infinitely long polynomial, right? Think about if a was 0. A could change depending on what series we're talking, or what power series we're talking about. So what if a is 0? We would have C0 plus C1 times x plus C2 times x squared plus C3 x cubed. Okay, maybe now it looks, these are both polynomials. Maybe this is more clear to you. Um, so what are the c's? The c's are just the coefficients of my kind of infinitely long polynomial, right? This is, very similar to having 1 plus 3x squared plus 7x to the fourth or something, right? This is a polynomial with a finite number of terms, and this is, I wouldn't call this a polynomial, but it's analogous. It's very similar, okay? So this thing, this kind of, it's not really a polynomial, but looks very similar. We call it a power series. Okay. But I want you guys to kind of start off with this most general form, okay? So this is a power series, and we would actually call this the power series centered at A. I'll explain what this centered at A means, but it's when we have x minus something, the A is going to be the center of our power series. Okay, so this power series is centered at A. And we can ask, just like over here, we ask some questions about this series, we can ask some questions about this series. And they're very similar to these questions over here. We could say, does it converge? Okay. Just like when we're asking this question, the answer to this question really depends on the series, right? We have all these different tests for these different types of series. What about over here? What could change depending on the series? What can affect the series? So obviously the CNs can affect it, but also the X can affect it, right? Maybe my power series will converge for some X, but not others. Okay, so maybe we could ask, where does this series converge? Meaning, for what values of X? And then maybe the last question, just like over here, we ask, what is the value of this series? We could ask, okay, what does this series equal? Okay. So these are the important topics we want to cover for power series. All right. So now that we've seen this general form, I think it'll be easier if we consider a specific form first. So let's consider, okay, so again, the general form is this, starting at 0. Okay, let's consider, let's say Cn equals 1 for all n and A equals 0. Then what would we get? We would get this power series x minus 0 to the n, which is just x to the n. Okay, so now it's a lot simpler, right? These power series can be very simple or very complicated. All right, and then we could just write out a couple terms of this. This power series would be 1 plus x squared plus x cubed, so on. Okay. Now, okay, that's pretty simple. But look at this series. What does that look like to you from sections 11.2 through 11.6? This kind of looks like the geometric series, right? If this was just some constant r to the n, that would be a geometric series. And what do we know about geometric series? Um, Geometric series should converge when this r value is less than the absolute value is less than 1. So same thing should be true for my power series. Should converge. Okay. And then what do I know about the sum of the series? And this is kind of the answer to questions 1 and 2, right? Yeah, it's going to converge, and it's going to converge when the absolute value of the x is less than 1. So we could say this is like questions 1 and 2. And then what about question 3? What does it equal? Well, for the geometric series, I'll kind of do this off to the side. When I had, let's see, I had a bit different form for my geometric series, right? I had Rn minus 1, n equals 1, okay? And when I had that form, the sum was 1 over 1 minus r. Well, it turns out that if I started at 0 and have r to the n, I can use the same formula. The sum is still 1 over 1 minus r. Okay, so let's see. Now let's apply that to my series, my power series over here. The value, if I plug in x for some x in here, the value of my series should be 1 over 1 minus x. Okay, so the value really depends on what x I plug in, right? I plug in a specific x and I get a specific value out. So what does that sound like? plugging in an x and getting one value out. Sounds like a function, right? So it turns out that when a power series converges, we could think of it as being not equal to a number, but equal to a function. Okay. So, and this is true. This is true for this power series on the interval -1 to 1, but it's true for all power series when they converge. Okay. So this is a function. This is uh, the function 1 over 1 minus x. So in between -1 and 1, my power series is equal to this function. Okay. And let's, maybe to make it a bit clearer, let's plug in some values to this and see what's going on. Okay. So again, I'm considering x to the n. Let's just plug in some values. Let's say this is my value of x, and then this is my value of my series. X to the n. Okay, so how about -3/4? Okay, so I've made this table of values here. So if I plug in x equals -3/4, my series value is 4/7. Okay, and I'm just calculating that from my 1 over 1 minus x here, my sum formula. And then if I plug in -1/2, my series should be equal to 2/3. If I plug in 0, my series should be equal to 1. And then what's happening as I get close to 1 over here, when I'm really close to 1 at 99 over 100, I plug that in. I should get 100 from my series. Okay. So if I graph this thing, what would it look like? Let's say that's 1, that's -1. Okay. Okay, so when x is 0, my series is equal to 1. As I come over close to 1, my series is going to shoot up to infinity. And then what's going on over here? My series is decreasing, and this should be right around 1/2. We can't say it's equal to 1/2, but it's getting close to 1/2. Okay, so these are the values of my series. Okay, and what have I done? I've basically plotted some points and then connected them. Okay. And it turns out if, okay, I graph the points of this and connect them, I'm going to end up with just this function. Okay. So when this series converges, okay, on -1 to 1, it converges to these values. So on this interval, this series is completely equal to 1 over 1 minus x. Okay. Now there's a bit of a difference, right? Because let's see, 1 over 1 minus x, it doesn't exist. It's not defined at 1, right? And let's see, so it would break right here at 1, but then it would exist over here. So this function would, this 1 over 1 minus x would exist over here. Okay, so maybe it looks like that. And then similarly on this side of -1, this function still exists, right? This function keeps going. Okay, but this series only exists between -1 and 1. So for the series doesn't exist outside this interval. Okay. So what does that mean? When we have a series, if it converges, a power series, if we have a power series and it converges, it's going to be equal to some function where it converges. Okay. We call this area where the series converges its interval of convergence. Okay. So on this interval of convergence, my power series is going to be equal to some function. And in this case, this power series is equal to the function 1 over 1 minus x. Now, this function might exist outside the interval of convergence, but my power series is only equal to it inside the interval of convergence, okay? Now, just some notes will kind of clarify this stuff a bit later, but look at this interval of convergence for this series x to the power n. It's nice and symmetrical, right? It goes from -1 to 1. And let's see, it's centered around this point, x 0. And let's see, if we think about our power series, remember the general form. Let's see, we have, here it is up in the top left, Cn x minus a to the power n, right? Where we said a was the center, okay? So this series, maybe it'll be a bit clearer if I write it like this. Same thing, right? Okay. So I have this center here. This, in our case, this center is 0. So, and then my interval of convergence is kind of symmetrical around this point 0. And that's always going to be the case. Whenever I have a center for my power series, my interval of convergence is going to be right around this center. Okay, so it's going to be half on one side, half on the other. Okay, so that's an important trait. And how big can this interval of convergence be? Well, it turns out there are 3 possibilities. Okay, so let's say I have, this is my number line. Okay, this is my general form of my power series. Okay, so here's my A. It turns out there are 3 possibilities. The series might converge at just A. Okay. So it only converges at A. Okay. Meaning the interval of convergence is just a single point. Okay. If we go back to this interval of convergence, okay, the distance it goes out to one side, we could call that the radius of convergence. All right. So if the series converges only at a single point, we could say that the radius of convergence is 0. R equals 0. Okay. What's the next possibility? The next possibility is, okay, it's some finite interval. So we have a positive radius of convergence, and our series converges on, let's see, it converges from A minus R to A plus R. All right. So my second possibility is my series converges everywhere in between here. Okay, it's power series are nicely behaved in that there aren't going to be any gaps. Like it's not going to converge here and then not converge here and then converge here. It's going to converge on the whole interval between A minus R to A plus R, and then it might converge at the endpoints too, right? It might converge. Maybe it converges here at A minus R and A plus R, or maybe just one of those. So we could say it converges for, let's see. So what have we said here? When the distance between x and a, so if like I pick an x in here, if the distance is less than the radius of convergence, meaning my x is in less than r away from a. Okay. If the distance, let's see, x minus a is less than r, my series is going to converge. And if the distance between x and a is greater than r, okay, so if my x is out here, my series is going to diverge at this x, okay? And then we could have, it could converge on, let's see, okay, it can converge at both endpoints. Maybe it only converges at one endpoint. Uh, maybe it doesn't converge at either endpoint, or okay. So the endpoints, we got some possibilities as well. All right. And then what's the third possibility? Okay, so what have we seen so far? Maybe it only converges at a single point, maybe it converges at this finite interval, or maybe it converges everywhere. Okay, so if it converges everywhere, let's see, what would the interval of convergence be? The interval of convergence would just be all of the real line, right? If I'm saying it converges everywhere, it would converge at A, it would converge everywhere on the number line, boom, 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 to the left and to the right. So the interval of convergence would be negative infinity to infinity. And then the radius of convergence would be infinity, right? So let's see, I have my A here. It goes off infinity to the right and infinity to the left. Okay, so let's see. These are all intervals of convergence. And I haven't, let's see, R greater than 0. Okay. All right, so let's just review. There are three possibilities from, like, when I have a general power series like this. There are three possibilities and only these three possibilities. The series converges at a single point A. It converges on some finite interval. Okay, and then we need to check the endpoints, or it converges everywhere. So going back to our original first two questions, we ask, does it converge and where does it converge? And so we're kind of answering two. If we're going to ask question number one is the first one we should ask. Well, from our three possibilities, we see it, our power series always converges at least one point, right? There's no possibility for it to diverge everywhere. I haven't listed that. And I can show you why in a minute. But my series always converges at least one point. Okay, so that answers number one. And then we see that where does it converge? Well, it's either going to converge at the center, at this A value, a finite interval around the A, or it's going to converge everywhere. And I'll give you a tool to figure out that interval in a moment. And then we ask, what does the series equal? Well, on the interval of convergence, it's going to equal a function. It's going to equal some function f of x. So what type of functions could our series equal? Well, they could equal some very familiar functions. For example, let's look at this series. Okay. X to the n over n factorial. Okay, is this a power series? Remember, my power series, my general formula for my power series is this. Okay, so does this match up with my general formula for a power series? Yeah, and maybe to make it a bit more clear, I could, write it like this. Okay. These two things are the same, right? Top and bottom are the same. Okay, so what's my Cn? My Cn is equal to 1 over n factorial. Okay, so that's my coefficient in front of my powers of x. And then what's my A? Where's my series centered? It's centered at A equals 0. Okay, so yeah, this is a power series. And it turns out that this power series is going to be convergent everywhere. Okay, so answering the first two questions, one we can kind of forget about because our series is always going to be convergent at least at A. So let's skip right to two. It's going to be convergent everywhere. And again, we haven't seen why, but I'll give you a tool later. And what I wanted to show you is this question 3. What does it equal where it's convergent? Well, it turns out that this power series is exactly equal to the function of e to the power x. Okay, so we're very familiar with e to the x, right? We've differentiated this, we've integrated this. All right. So it turns out if I take any number and plug it into this series, I'm going to get the exact same value as e to that number. Okay. So if I did like, what I mean is if I plugged 1 in here, I plugged 1 into my series. This series is going to be convergent. I could figure that out by ratio test, right? This series is going to be convergent, and it's going to have a sum. And it turns out that sum is going to be exactly equal to e to the power 1. Okay, so if I plug 1 into my series, it's the same as if I plug 1 into this function here. All right, and there are a lot of familiar series. We can develop series for a lot of familiar functions like sine of x and cosine of x, okay, and all our polynomials, and pretty much any function we're familiar with from calculus, we can make a power series for. Now, the series for sine of x, maybe it's not convergent everywhere. Maybe it's only convergent on some interval, okay? But we'll deal with that in a little while. So before we move on, I want to explain why. Let's see, before we move on, I want to explain why our power series is always convergent at least the center. Okay, so let's talk about that. So going back to our general form of a power series, okay, let's write out a couple terms. This is going to be equal to C0 plus C1 x minus a to the power 1 plus C2 x minus a squared plus blah, blah, blah. Okay, what happens if I plug in x equal to a? Meaning, what happens if I evaluate this power series at x equals a? Okay, well, let's see. This term, it would be a minus a, so 0. So I'd have C1 times 0, okay? And then this term would be 0, and all the other terms will be 0, right? So I would just end up with C0. So my series is convergent, right? It's just a single number, all right? So that's going to be a convergent series. So I can see why my series is always convergent at least at that center. It's always going to be convergent at a, because if I plug in x equals a, all the terms cancel except the first one, all right? So my series is always going to be convergent at a. Now, my series, depending on what these CNs are, my series might be convergent at more than a. It might be convergent on an interval, or it might be convergent everywhere. But we can see why it's at least convergent at x equals a. All right. So that's a quick justification. And the other two possibilities are a bit more complicated, but we can see why our series is at least convergent at the center. All right, so just to reiterate, this is what we know about convergence of our power series so far. So I have the general form of my power series. It's always going to be convergent at a, at the very least. And then there are 3 possibilities. It's only convergent at a, meaning the interval of convergence. How do I write a single point as an interval? It's just braces with the center a in the middle, okay? And then the radius of convergence would be 0, has 0 radius. Okay. What's the second possibility? It's converges on some interval centered around A. Okay, so it has a positive radius of convergence. Let's call the radius of convergence equal to C. So then my interval of convergence is going to be one of these 4 intervals. Like it's going to be A minus C to A plus C with, closed braces. All right, so what do these closed braces mean? It means like if I plug in this value to our x, for our x, my series is going to converge at that value. Okay, that might not be the case. It maybe it'll converge for every value in between these two, but it doesn't converge at the endpoints. Okay, so it might converge at both endpoints, it might converge at neither of the endpoints, or it might converge at one or the other. Okay, so these are my four possible intervals. And then what's the third possibility? My series is going to converge everywhere, meaning the interval of convergence would be negative infinity to infinity, and then my radius of convergence would just be infinity. All right, so this is the information for convergence of series. And then, like we said earlier, okay, on the interval of convergence, my power series is going to be equal to some function. Okay, so on the interval of convergence, okay, this power series is going to be equal to some function, and that function might be a familiar function, like we said it's earlier. It's a familiar function like e to the x or cosine of x or something like that. Maybe this power series, I can write it as one of these functions on that interval. Maybe it's not a nice function. Maybe the only way to write it is, okay, I just say, let's see, f of x is just equal to the power series itself, meaning, okay, this power series is equal to a function on its interval of convergence, but the only way to write that function is just as the power series. Okay. All right. So the point that I want to drive home is this. Okay. On the interval of convergence, this power series is going to be equal to some function, and it might be a familiar function. So really, these two slides are kind of the important information. We have a power series. It's going to converge at least one point. It might be convergent elsewhere. And then when it's convergent on that interval of convergence, it's going to be equal to some function. So now let's start talking about how we figure out all these properties. First, let's talk about um, interval of convergence. How do we find interval of convergence? Okay. Well, it turns out when our power series is either going to be absolutely convergent or divergent. Okay. So we have this really great test for, well, I shouldn't say absolutely convergent. Let's see. Okay, let's start talking about how we find these properties. How do we find the interval of convergence for a power series, and how do we find what function it's equal to? Let's start with the interval of convergence first. Okay. So let's say I have my power series. How do I find the interval of convergence? Well, again, we won't go over why in this course, but it turns out that, okay, if a power series converges, let's say it converges on this interval, it turns out it's actually going to be absolutely convergent inside this interval. So what do I know about absolute convergence? Let's see. Ratio test is really closely related to absolute convergence, right? So it turns out, let's see, if I do ratio test to my power series here, okay, what am I going to get? So ratio test, I want to start by figuring out what this is. So let's see, that would be, simplifying this, I would get Cn plus 1 over Cn times this, right? So it turns out that when this is less than 1, okay, when the limit is less than 1, Okay. If this limit is less than 1, then series is convergent there. Okay. So my interval of convergence, okay. Now, when is this limit less than 1? That depends on the x, right? Let's see. This is a constant and these are changing. So, this Cn plus 1 over Cn has a limit. And then if that limit's less than 1, that really depends on what x is, right? So interval of convergence is going to be all x's that make the above limit less than 1. Okay. So that gives us the stuff inside the interval. Okay. And then to figure out if the endpoints are included, we have to test those endpoints individually. Okay. So maybe it's, again, maybe it's the closed open, or maybe it's closed closed, and so on. So the ratio test tells us all these points in the middle, and then we have to look at these endpoints individually. Okay. So let's see an example. I think the most clear way to do this is just with an example. All right, so let's look at a specific example finding interval of convergence. Okay, so let's look at the power series. And let's try and use this ratio test method to find our interval of convergence. Okay, so let's see. I do ratio test. I just apply ratio test to my power series, just like I would with a normal series. And remember, when I do ratio test, I'm looking at absolute value of everything inside my series, an plus 1 over an. Okay. So when I do absolute values, I can ignore any negatives, right? So this becomes, let's see, okay. And then let's simplify this. X to the n plus 1 over x to the n just equals this. Okay. And let's keep the absolute value bars. Okay, so I want this limit to be less than 1, right? And I know the limit of n plus 1 over n, that limit is 1. So what do I need? I need x to be less than 1. Okay, so let's see, that means my interval of convergence is going to be -1 to 1. All right. So this tells me my series is at least convergent on, you know what, let's see, so my power series is at the very least convergent on -1 to 1. Okay. So my center of my power series is at 0. My power series is convergent all in here, all the way to 1. And now I need to test the endpoints. Okay, so how do I test the endpoints? What am I going to do? I'm just going to, let's kind of clear some space here. Okay, so I've done ratio test to figure out it's at least convergent on -1 to 1. Okay, how do I test the endpoints? I'm going to plug -1 into this series, and I'm going to plug +1 into this series. And where am I going to plug it in? I'm going to plug them in for x. Okay, so let's see. Let's try x equals -1. Okay. So I get, when I plug -1 in for x, I get -1 to the power n. Okay. So I got two -1s to the power n, right? So that's, I can put those together and get that as 2n. N. Okay. And so now I have -1 squared to the power n, right? So this is always 1. So really this series simplifies as n. Okay. Now, is this series convergent or divergent? Well, it's definitely divergent, right? So I don't want to include the point -1. Okay. What about +1? Let's do the same thing for +1. So I plug in 1 for x. And then I would end up with, after I simplify everything, I would end up with this series. And now I ask, okay, does this series converge or diverge? Well, it's still going to diverge, right? This looks like an alternating series test, but the terms, the terms inside don't go to 0. So I could say this diverges by divergence test. Okay. So this endpoint doesn't converge either, so I don't want to include that endpoint. So my interval of convergence is -1 to 1, not including the endpoints. Okay, so open parentheses on both of these. And then what is the radius of convergence? Well, once I have my interval of convergence, I just divide, I find the length of this interval and divide it in 2. Okay, so the radius of convergence is 1, right? Because 1 is the distance from here to here and here to here. Let's do one more example, and let's do this important power series we mentioned earlier. Let's do this one. X to the power n over n factorial. So let's find the interval of convergence for this series. Okay. So again, what am I going to do? I'm going to do ratio test. I need to do an plus 1 over an. Okay, this is my an plus 1. I need to divide by an, which means multiplying by the reciprocal. And let's simplify. Let's see, this should be n factorial over n plus 1 factorial. That's going to simplify to 1 over n plus 1. And then x to the n plus 1 over x to the n, that equals x. Okay. So what is the limit of this? Okay. Well, I'm going to treat x as a constant. Okay. And then what's the limit of 1 over n plus 1? It's 0. Okay. So for what x is this limit less than 1? I want to figure out, when is this less than 1? Well, it turns out that no matter what x is, the limit is less than 1, right? Like if, let's say, x equals 100,000, the limit is still going to be 0. Okay. Let's say x is a billion, the limit is still going to be 0. So no matter what x I plug in, the limit is 0. Okay. So that means the limit is less than 1 for all x. So my power series is going to be convergent for all x. Okay. So how do I write my interval of convergence? -infinity to infinity. Okay. So interval. What's my radius of convergence? Well, that's just infinity. Okay. Okay, so let's try one more example of finding the interval of convergence, and let's try it for this power series. Okay, so again, I want to try a ratio test. Okay, so I try a ratio test, and let's see, first I need to find an plus 1 over an. Okay, so that's going to be, let's do our an plus 1 first. Dividing by an means multiplying by the reciprocal. Okay. Simplifying. Okay, 4n over 4n plus 1 is equal to 1 over 4. N to the fourth over n plus 1 to the fourth. And then what do I got? X minus 2 to the n plus 1 over x minus 2 to the n. That's x minus 2. And now I'm looking for the limit of this thing. Let's see, what's the limit of this? I can pull a constant out. The limit of this thing is 1. And then what's the limit of x minus 2? I treat that as a constant. Yeah, x minus 2. Okay. So I want to choose x's so that this whole thing is less than 1. So what do I want? I want 1/4 times absolute value of x minus 2 to be less than 1. Okay, and now it's all about solving this inequality. So I want to get x by itself. First thing I do, multiply this 1/4, multiply both sides by 4 to cancel out 1/4. So I want x minus 2 to be less than 4. If I want x minus 2 to be less than 4, that means I want x minus 2 to be less than positive 4 and greater than negative 4, right? Now, last step to getting x by itself, I add 2 to both sides. Okay. So this means my interval of convergence is from, oh, and this should be negative 2. From 6 to negative 2. Okay, and notice this is an interval centered around x equals 2, right? So again, this 2 is my center. All right, what's the radius of convergence? Let's see, 4, right? And then what about the endpoints? What's going on in the endpoints? I need to check the endpoints. Okay, if I plug negative 2 in, okay, let's see what happens at the endpoints. Let's look at this series. Well, simplifying that, that is the series negative 4 to the n over 4 to the n to the fourth. Okay. What's negative 4 to the n over 4 to the n? That simplifies as, okay. Now, is this series convergent or divergent? Well, it's a convergent alternating series, right? So it's convergent. Okay. So that means I want to include x minus 2 or x equals negative 2 into my interval of convergence. Okay. So I want to include x equals negative 2. Now I need to check x equals positive 2. Okay. I plug that into my series. I plug this in. What's 2 minus 2? It's 0. So I get 0. What is this series? This is just 0, adding up 0 infinite amount of times. Is that series convergent? Yeah, it's convergent. It's equal to 0. Okay. So I want to include x equals 2 in my interval of convergence as well. Okay. So let's see, going back to my original problem, I want to include these endpoints. So my interval of convergence is going to be -2 to 6, brackets on both sides. Radius of convergence is 4. All right, so that covers all the ideas from 11.8. I'll put up a problem video where I work through more problems as well, but let's recap the information. So we have a power series, Cn x minus a to the n, where all these Cn's are coefficients. We know that the power series is always going to be convergent at this center when x equals a, okay, because then we'll just have a bunch of zeros. C0, our first coefficient, plus a bunch of zeros is always going to be convergent. Then there are three possibilities for convergence. Number one, the series is only going to be convergent at that center, only at x equals a. Possibility two, it's convergent on a finite interval centered around a. So let's say our radius of convergence is c, then our interval of convergence is going to be one of these four intervals centered around a. It's going to either be a minus c to a plus c, brackets on both, same thing, parentheses on both, or maybe one parentheses, one bracket, and vice versa. Okay. Or then we have a third possibility where the series is going to be convergent everywhere. So my interval of convergence would be negative infinity to infinity, and my radius of convergence would be infinity. Okay. How do we find this interval of convergence? We do the ratio test, and then we're looking for all the x's that make our limit less than 1. Okay. So that those points are definitely going to be included. And then maybe the endpoints will be included, but we need to test those endpoints individually. On the interval of convergence, the power series is equal to some function f, and it might be a familiar function like e to the x or cosine of x, something like that. Or maybe we can only write it as, we'll just say f of x equals the power series. Okay, so maybe there is no simple representation. But on that interval of convergence, we can consider the power series to be a function of x. And how do we find the function of x? Well, we'll deal with that in later sections. We're not going to deal with that in section 11.8. Okay. So all we need to know from 11.8 are these ideas and how to find the interval of convergence. Okay. Hopefully this video was helpful, and keep an eye out for the problem video.